You ever stop and think about what's actually happening inside your computer or your phone? I mean, really going on under the hood? It turns out most of our devices are running with not one, but two different kinds of brains. And while they work together, they think in completely fundamentally different ways. So let's dive in and really unravel the story of these two powerhouse processors, the CPU and the GPU.
And that really brings us to the big question here, doesn't it? Why? Why would anyone go through all the trouble and expense of designing and installing two separate processors? Why can't just one of them do it all? Well, to answer that, we've got to meet our two main characters.
So first up, we've got the CPU, the central processing unit. And to really get what this thing is all about, I want you to picture a master chef in some fancy, high-end restaurant kitchen. This chef is an absolute genius. They can create any complex, one-of-a-kind dish you can possibly imagine.
Okay, so technically speaking, the CPU is what we call a general-purpose processor. But the most important words here are low latency. And that's really just a way of saying its number one job is to get a single task started and finished as fast as siliconly possible.
That's just like our master chef, right? When you order that really complicated signature dish, the chef doesn't mess around. They focus all their skill, all their attention, and they get that one single perfect plate out to your table in just a few minutes. That is the CPU in a nutshell. It's all about speed and precision on one big task at a time. And how does it pull this off? Well, a typical modern CPU might have something like 8 cores. But you shouldn't think of these as just 8 extra hands. No, think of them as 8 incredibly powerful, highly trained master chefs. Each one is a complex powerhouse, ready to tackle any difficult recipe you throw at it. All right, now let's meet the second brain in our machine, the GPU, or graphics processing unit. And if the CPU is that master chef, the GPU is, well, it's something completely different. It's a massive, sprawling factory assembly line. You see, the GPU is a specialized processor. It was literally born to do one thing and do it incredibly well. Handle thousands, even millions of simple, repetitive tasks all at the exact same time. Its whole design philosophy isn't low latency, it's high throughput. Its goal isn't to get one thing done super fast, but to get a million things done at the same time. Think about that assembly line again. It's not designed to make one perfect artisanal car. No way! It's designed to pump out 10,000 identical cars every single day. That's throughput. And that is the absolute magic of the GPU.
And just look at this. This is how it achieves that massive scale. Instead of 8 powerful cores, a high-end GPU might have over 10,000 simple cores. These aren't master chefs. These are thousands upon thousands of factory workers. Each worker can only do one simple thing, like tighten a single bolt. But together, they can build an entire car in minutes. The difference in scale is just staggering. So we have a chef and we have an assembly line. They have totally different goals, right? And that means, of course, that they have to be built from completely different blueprints. So let's pop the hood and look at the actual schematics to see how these different goals create two fundamentally different pieces of hardware. This chart just lays it all out perfectly. You've got the CPU, our chef, aiming for low latency with just a few complex cores. And then the GPU, the assembly line, targeting high throughput with thousands of simple ones. But look at the instruction method. The CPU uses something called MIMD. That's multiple instruction, multiple data. It means each of our chefs can work on a totally different dish at the same time. The GPU uses SIMD, single instruction, multiple data. That means every single factory worker is performing the exact same action, just on a different part. That difference changes absolutely everything about how they're built.
So let's dig into that circuitry. A huge chunk of the CPU's silicon real estate is dedicated to what's called control logic. This is the part that makes smart decisions, handling if this, then that scenarios, predicting what to do next. It's the chef's brain, the part that allows them to taste the sauce and decide, needs a little more salt. The GPU, on the other hand, dedicates almost all of its space to ALUs, or arithmetic logic units. These are basically just tiny, simple calculators. The assembly line worker doesn't need to think or adapt. They just need to do basic math over and over again at lightning speed.
And this whole different philosophy extends to how they handle data. The CPU has a large private cache. Think of it like the chef's personal pantry, right next to their station, with every single ingredient within arm's reach for instant access. But the GPU doesn't have time for that. It has to feed thousands of workers at once. So instead, it has a massive, wide memory bus. Picture a giant conveyor belt that's constantly dumping mountains of raw materials onto the factory floor for everyone to grab.
Okay, so we have a brilliant, adaptable chef and a massive brute force assembly line. We've seen their blueprints. Now let's see what actually happens when we give them real jobs to do, jobs that affect our everyday computer use.
The CPU, our master chef, is amazing at any task that requires complex logic and constant decision-making. Things like running your operating system, managing your files, browsing the web, these all require a fast, adaptable mind. You simply can't run Windows or Mac OS on an assembly line. You need a manager, a decision maker. That's the CPU's job.
The GPU, our assembly line, is built for the number crunchers. I'm talking about any task that can be broken down into thousands of identical parallel calculations. Calculating the color of millions of pixels for a video game, training an AI model on huge datasets, rendering complex video effects. This is what that assembly line was built for.
And this chart just shows the difference so clearly. If you asked our brilliant master chef, the CPU, to paint every single pixel in one frame of a game, one by one, it might take 180 milliseconds. But the GPU's assembly line, where every single worker core calculates just one pixel at the same time, it can do it in only 16 milliseconds. That is literally the difference between a choppy slideshow and perfectly smooth, immersive gaming. It's all about using the right tool for the job.
So by now, you might be thinking this is some kind of competition, CPU versus GPU. But that is absolutely the wrong way to look at it. The reality is that modern computing isn't a fight. It's more like a finely choreographed dance. It's a perfect partnership.
Honestly, this is the single most important thing to take away from all this. It is not one against the other, it's the two working together. The chef can't build a factory, and the factory can't come up with a new recipe. They absolutely need each other. So here's a quick look at how it actually works. When you launch a game, the CPU is in charge. It runs the operating system, it understands your mouse clicks, it acts as the manager. It tells the graphics driver, which, by the way, is also running on the CPU, to translate the big picture commands into thousands of simple instructions the GPU can understand. And then, only then, does it hand that massive parallel job off to the GPU's assembly line. The CPU is the brain of the operation, the GPU is the muscle. Which kind of leaves us with one final big question. We've seen how they are incredible specialists, a brilliant chef, and a massive assembly line. But as things like AI and virtual reality get more and more complex, demanding both rapid, smart decisions and massive parallel processing, will the line between them start to blur? Are we going to see the chef learn some assembly line tricks and the assembly line start to think for itself? Well, that's probably the next chapter in the amazing story of computing.